Okay, we're in chapter 15 now. We're almost at the end. And chapter 15 is talking about three topics that are kind of combined into one. Acids, bases, which are usually go together, and salts. And we'll see how salts fit in with acids and bases in the chapter. It involves the process of forming ions in solution, if that gives you a clue. Before we start talking about what acids and bases and salts are, we're just going to start off by introducing water. And what happens to water inside just of any liquid state of water? If you have water, pure water doesn't exist as just H2O molecules, not purely. Water reacts with itself to form ions. This is a process called autoionization. And water will react with itself or break apart to form two different ions, a proton called a hydrogen ion and a hydroxide ion. So I'm going to draw that here. So here's a Lewis structure of water. We have HOH, or H2O, right? There's the 4 electrons. So this is a Lewis structure of water. When water reacts with itself, we can either show one molecule breaking apart, and if I do that, I'm going to show the molecule breaking apart between the hydrogen and oxygen bond right here. So that bond's going to break. When that bond breaks, this pair of electrons that was shared between hydrogen and oxygen is going to be pulled toward electronegative oxygen completely, and that bond is going to sever. So we're going to push these electrons over, break this bond, and we're going to end up forming hydrogen ion, also called a proton, and hydroxide ion, called hydroxide. All right, so the hydrogen ion, let's go ahead and label. This is called a hydrogen ion. It's really hard to write on these things. Hydrogen ion. The other name that chemists usually refer to H plus as is a proton. Why do we call H plus a proton? Well, if you look on the periodic table of elements, the atomic number for a hydrogen atom is 1, which means there's 1 proton in the nucleus. So for a neutral hydrogen atom, there's 1 proton and 1 electron, and overall the atom's neutral. If you remove the electron from the shell, you've ionized, it's lost an electron, and now all that's left is the 1 proton in the nucleus. So a hydrogen atom that has lost its 1 electron is a hydrogen ion, cation, but it's technically a proton. So what we're seeing here is that when water self-ionizes, it breaks in two to form a proton. So a proton comes loose and you're left with hydroxide. So let's go ahead and label hydroxide here. We've seen hydroxide before, so that's the anion. When chemists talk about acid chemistry and base chemistry, we're going to talk about 3 different definitions of acids and bases. Classically, a substance that liberates hydroxide ions was known as a basic substance. So the hydroxide ion in water is primarily what's responsible for the basic properties of water. So whenever you see hydroxide, think base. Also, when we talk about acids, anything that liberates or generates a hydrogen ion in a water solution or releases a hydrogen ion or a proton in solution is thought of as being an acid when dissolved in water. So the proton, or the hydrogen ion, is always going to be characterized as being something that's acidic, or when there are many protons released into a solution, it's an acidic solution. Alright, so this is the autoionization of water. Water reacts, and notice the way I wrote that it reacts here. Let me go back and change colors. Alright, when I showed the water reacting, notice I used something called the equilibrium arrow. We've seen this arrow before. You can also draw it this way. An equilibrium arrow exists when a reaction goes forwards, but it also goes reverse. So the reaction generates the ions, but then in the reverse direction, those ions can react together and reform water. Alright, what's another way that I can show water autoionizing? Rather than showing it reacting by just splitting apart, I can show two water molecules reacting with each other. So if I have HOH, one water molecule, and I have another HOH, the second water molecule, I can show that these will react together to show a different form of the same autoionization reaction. In this case, this time we're going to take a lone pair of electrons from one oxygen. Remember how those lone pairs can hydrogen bond with another water molecule? Gives the properties of water having a really high boiling point. Instead of hydrogen bonding, suppose that these electrons reach down and bond to another hydrogen atom from another water molecule. When they bond hydrogen and can only get one bond, this bond will break. So what we're going to do here is we're going to add a third hydrogen atom to one water molecule and remove a hydrogen atom from another molecule. Effectively, when one water molecule reacts with another water molecule, we end up forming H3O plus hydroxide minus. So the other way I can show the autoionization of water is two water molecules reacting together, ionizing to form H3O plus, which is called the hydronium ion. The hydronium ion. And then also, once again, we form the hydroxide ion. I'm running out of room there. So we have the hydronium ion and a hydroxide ion. Notice that I wrote hydronium in red. Whenever the water molecules react with each other, two water molecules autoionize, one of the water molecules picks up a hydrogen and a positive charge. So it goes from water to H2O to H3O plus. Basically what we're saying, and I'll just show this here, if you have H2O, if you add a plus charge from a proton and you add an extra hydrogen atom, you effectively have hydronium ion. The way you get that is by reacting, here we go, a proton adding to water. So when a proton reacts with water, that reaction forms hydronium ion, H3O plus. H plus H2O yields H3O plus. How did I get that? Add the two hydrogens together, add the charges together, a plus one, and this is a neutral charge. So all together, we end up getting a plus one charge and H3O. So why am I showing you this? In a water solution, if a compound like water was to split apart to form a proton and a hydroxide ion, that proton is very, very reactive. It's unstable in water, and it immediately will react with the water to form the hydronium ion. So even if we think about this self-reaction occurring, or the reaction occurring between two water molecules, as soon as a hydrogen ion is formed, or a proton is formed, it will immediately react with another water molecule, and it will form a hydronium ion. So basically, or effectively, what we can think of is that if I ever use the symbol H plus for a proton, and I'm in water solution, So if we ever have a proton floating around in water solution, we can call it a proton if we like, but we know that it will immediately react with water. So effectively, we can think of that being the same thing as the hydronium ion. The hydronium ion. All right, so these two in water solutions for us are going to be interchangeable in this chapter. If I ever say H plus and we're in water solution, you can also replace that with H3O plus and vice versa. Now, one thing I want to point out, and this is when water reacts with itself. So if you had a glass of water, do you only have H2O molecules in that glass of water? The answer is no. If it was pure water, it would still react with itself or auto-ionize, and you would also have protons and hydroxide ions in that mixture. You would have mostly water molecules, but you would have some ions in solution. So the question is, if the proton is an acidic atom or ion, and the hydroxide is a basic ion, is water acidic or basic? The answer is that water is actually neutral. Water is neutral. It's not acidic or basic. In fact, the word that we use to describe water is this word called amphoteric. And basically what amphoteric means is that water can act as an acid or a base. So water can act as an acid or a base, but itself, water is neutral. Now, why is water neutral? Well, if we go back here, whenever water auto-ionizes, if we have 1 mole of water and itself auto-ionizes, we can look at this as a mole reaction, the mole ratios. 1 mole of hydrogen ion will form and 1 mole of hydroxide ion will form. Because we have equal amounts of the acid and the base formed, overall there's no net acid or base in the end. So overall they cancel each other out. We end up being neutral. So water is neutral, but it contains both acid and base ions in pure water. But what we've learned in class so far, in the last unit that we've been studying, is that many compounds dissolve in water and you can form solutions that have different properties. When different compounds are dissolved in water, what happens is the concentration of the hydrogen ion or the hydronium ion can change. And when that happens, you can change the acid-base properties of water. In order to quantify how much proton or how much hydrogen ion is in the solution, we calculate something called the concentration of the hydronium ion, or a concentration, this means it's the same thing, of the hydrogen ion. So remember, whenever I use the hydronium ion, that means the hydronium ion, it means the same thing as the proton. Now, why am I drawing brackets around the structure of this ion? The brackets mean the concentration of. So when I draw a bracket around anything, if I write a bracket around HCl, the brackets mean the concentration of HCl. So here we have the concentration of a proton, the concentration of hydronium ion in solution. Now, what concentration term are we going to be using? In the last chapter, we looked at many ways to define concentration. In this chapter, the main concentration term that we'll be using is molarity. So let me just remind you of so the concentration of anything, I'm going to put X. We're going to be using molarity. And molarity uses moles per liter of solution. So the molarity of anything is always the moles of anything, that substance, divided by the liters of solution. Alright, so it's moles per liter. So what we're going to be looking at is we're going to be looking at the concentration of hydronium ion or hydrogen ion in solution. And as that concentration changes, we can change the acidity or basicity of a water solution. This is going to bring us to pH. So what is pH? What does the P stand for? Have you ever asked yourself that? Well, there is more than one theory about what the P stands for, but a lot of people think it's the German word for power starts with P. So it means a lot of people think that pH means the power of the hydrogen ion, and we'll talk about what that means in a second. So pH is a parameter in chemistry used to quantify the concentration of hydronium ion or hydrogen ion in solution. Like I said a second ago, we know that water can react with itself to form hydronium ion, which is an acidic ion, and hydroxide, which is a basic ion. When pure water autoionizes, the concentration of hydronium ion is equal to hydroxide ion. And in pure water, we know what those concentrations are. They've been measured. It's 1 times 10 to the negative 7th molar. So 10 to the negative 7th molar hydrogen ion in a pure sample of water. 10 to the negative molar sample of hydroxide ion in a pure sample of water. All right. So the hydrogen ion and the hydroxide are equal in the neutral water solution. How do we define an acidic solution then? If you add something to the water, it dissolves or reacts with the water, and you liberate or produce more hydrogen ions than hydroxide ions, meaning the hydronium ion concentration is greater than the hydroxide concentration, then you have an acidic solution. The hydrogen ion concentration is greater than 10 to the negative 7th. Now let's think about this. What is a number greater than 10 to the negative 7th? If 10 to the negative 7th molar is a neutral solution, how do we get to be acidic? An acidic solution, we said, is a number greater than 10 to the negative 7th. Is 10 to the negative 8th molar greater than 10 to the negative 7th? No, that's actually smaller. It's 10 times smaller. But if you go to 10 to the negative 6, that's an order of magnitude greater in hydrogen ion concentration. So a hydrogen ion concentration of 10 to the negative 6th molar is acidic. 10 to the negative 5th molar is more acidic. So as we get to a hydrogen ion concentration greater than 10 to the negative 7th, we go from neutral to the acidic side of a solution. All right. Well, the opposite's true too. If you move from an equal concentration of hydroxide and hydronium, and then you add something to the water, it dissolves or something's liberated or it reacts with the water to form more hydroxide than hydronium, so you have more hydroxide than hydronium, what happens is you decrease the hydronium ion concentration. So as the hydronium ion concentration gets less than 10 to the negative 7th molar, your solution becomes basic. Now what's smaller than 10 to the negative 7th molar? Now we go to 10 to the negative 8th molar. That's an order of magnitude less. 10 to the negative 9th molar. That's 2 orders of magnitude less. 10 to the 2nd less. So we're becoming more basic. We've got more hydroxide ions in the solution than we do hydronium ions. All right. So what we see is we have these exponential numbers that are small, negative exponential numbers used to describe the hydrogen ion concentration in a solution. 10 to the negative 5th, 10 to the negative 6th, to the negative 7th, 10 to the negative 8th, 10 to the negative 9th. All of these powers of 10 with negative exponents. Well, instead of expressing the concentration of the hydrogen ion as a large exponential number, some number to the power of 10, it was considered much more convenient to drop the power of 10, so 10 to the negative x, and just say what the x is. So if it was 10 to the negative fifth, just say 5. So basically you're taking the log of the number. The log just means the exponent. So the word logarithm or log is the exponent of a base 10 number. So if I say 10 to the 6th, the log of 10 to the 6th is the exponent 6. Now, if I take the negative log of a number, I take the negative of the exponent. So if my number is 10 to the negative 6th, the negative log of that is 6, right? So log is just a fancy term used to describe an exponent of a base 10 number. Well, it turns out that when you report the hydrogen ion concentration of a solution, instead of writing it in straight exponential form with negative exponents, it was thought that it was easier to take out the exponent, the base 10, and to just show the log, the exponent itself. And because most of the exponents for hydrogen ions are so small, they're negative numbers, you put a negative in front of it. And this is how we came up, not we, but how the term pH and the mathematics of pH came up. The pH of a solution, how acidic a solution is the pH is the power of the hydronium ion or the hydrogen ion. It's technically the negative log of the hydrogen ion concentration. So this is an equation that you'll need to know. The equation is shown right here. The pH of any water solution is negative log of the hydrogen ion concentration. So for instance, if your hydrogen ion concentration is 10 to the negative 12th molar, what is your pH? Well, pH is the negative log of the exponent. So if the exponent is negative 12, it's the negative of negative 12, which is positive 12. All right? So the pH of the solution would be 12. So do you see how that works? All right. Well, it's not always quite as simple as it looks. Sometimes you might have to actually pick up a calculator. What if the hydrogen ion concentration, for instance, of a solution is 6.2 times 10 to the negative 4th molar? What would be the pH of that solution? Okay, the pH is the negative log of the hydrogen ion concentration. So the hydrogen ion concentration was 6.2 times 10 to the negative 4th molar. So would your answer be 4? No, because now you have a number in front of the base 10. When there's a number in front of the base 10, usually the number is slightly less than the negative of the exponent. So something slightly less than 4. What we're going to do is we're going to grab our calculator. Whenever you calculate a log, or a pH, you're always going to know how to use your calculator. Sometimes if you put in negative log, so you're going to press the negative sign and then log in order to solve for the pH here. Sometimes some calculators, parentheses will go ahead and pop up. Mine does pop up that way. You'll always want to put the entire term for the hydrogen ion concentration inside of parentheses. Like I said, most of the computers, the parenthesis pops up, so you're going to have to make sure you close after you put the entire term in. So I literally get my calculator out to solve the pH problem. Very simple. Negative log, parentheses, 6.2 times 10 to the negative 4th, close parentheses, equals. The pH of the solution, the negative log of the hydrogen ion concentration, is 3.2. So the number in front of a base 10 always lowers the exponent slightly. All right. We have some other equations that we can learn too. Remember that in a pure water solution, the the hydronium ion concentration equals the hydroxide concentration, and they were both 10 to the negative 7th. So if you take the negative log of 10 to the negative 7th, the pH of a water solution is going to be 7. It turns out that the pOH of the solution, you can take a power of any ion, the negative log of any ion, but the pH and the pOH of a water solution will always equal 14. Now that doesn't matter if it's pure water or if it's some solution of water. If the pH plus the pOH of a solution will always equal 14. Now what is the pOH? We know the pH of a solution is the negative log of the hydrogen ion or hydronium ion concentration. The pOH of a solution can be calculated the same way. It's the negative log of the hydroxide ion concentration. All right? So if I am given the hydrogen ion concentration, I can calculate the pH. And from the pH, because I know pH plus pOH equal 14, I can always calculate the pOH. It's whatever the difference between the pH and 14 is. So what does the pH have to do with acidity and basicity? Well, we said in pure water, the pH of pure water is 7 because the hydronium or hydroxide ion, the hydronium and hydroxide concentrations are 10 to the negative 7th molar. So the pH of 7 is pure water. Anytime you take a pH of any solution, if it's 7, you have a neutral solution. It's not acidic or basic. Now remember we said when the hydrogen ion concentration is greater than 10 to the negative 7th, like 10 to the negative 6th, 10 to the negative 5th, 10 to the negative 4th, basically when the pH, that's the opposite, is less than 7, because if you have 10 to the negative 6, that's less than 10 to the negative 7th in hydrogen concentration. The pH of 10 to the negative 6, the molar, is 6. So any pH less than 7 is going to be an acidic solution. And any pH greater than 7, because the hydronium ion concentration is less than 10 to the negative 7th, is going to be a basic solution. Now why is this? Remember that the pH is the negative log of the hydrogen ion concentration. So as the hydrogen ion gets bigger and you become more acidic in solution, there's more of that number, the pH will get smaller because of the negative number. It flips the scale. The pH scale is backwards in its direction from the hydrogen ion concentration scale. So let's practice using pH for a second then. What if I test a solution with a pH meter or some litmus paper? You've probably heard of litmus paper before. You've probably used it. It has an indicator on it that changes color. Usually in an acid solution, you would use blue litmus paper. And blue litmus paper turns to pink or to red when you're in an acidic solution. So acids always turn litmus paper red. Basic solutions always turn red litmus paper blue. Hence, this is the reason why I've been using red for acids and blues for bases. Typically, that's how chemists think. If you're on the blue side of the indicator, you're a basic solution. If you're on the red side of the indicator, you're an acid solution. So let's say that I pick up a piece of litmus paper, or like a pH meter, and I get a pH of 11. What does a pH of 11 for a solution mean? Does it mean I'm acidic or basic? Well, remember, a neutral pH is a pH of 7. So as I have a pH greater than 7, a pH greater than 7 means my hydronium ion concentration is actually less. So a number greater than 7 indicates a lower hydrogen ion concentration. This means that we have a basic solution. What if I have a pH of 2? What does a pH of 2 mean? Well, decrease your pH, as the pH gets lower or less than neutral, which is 7, that means that you have a higher hydrogen ion concentration, which means your solution is higher than than neutral. You have an acidic solution. So pH is less, just one more time for repetition, less than 7 are acidic. And pHs greater than 7 are basic. Okay. What are some properties of acidic or basic solutions? You know, sometimes chemists didn't used to use pH meters. Sometimes chemists could tell based on some of the properties of acids and bases whether or not the solution was acidic or basic or not. Some of the properties of acids are that they have sour tastes. They, of course, like I said, they can change the color of litmus papers and dyes from blue to red. They usually have the ability to react with metals like zinc and magnesium, active metals. Acids will typically react with carbonates like sodium carbonate, sodium bicarbonate to produce carbon dioxide. So if you put a carbonate salt into the acidic solution, you would see bubbles. So some of those are properties of acids. An example of an acid is that has a sour taste, for instance, is lemons, or maybe even citrus. We know that those are acidic, and they have that sour taste. What are some examples of bases? Some of the properties of bases. Bases aren't sour, they're typically bitter, caustic tasting to the tongue. Also, if you put them on your hands and kind of slide them around, bases are typically have a slippery or kind of a soapy feeling. Remember, they change litmus paper from red to blue, and they have an ability to interact with acids, so bases will react with acids, of course. So these are some of the properties of acids and bases. Where do acidic solutions come from? In water, they come from the excess hydronium ion. And what are basic solutions? When you have more hydroxide than hydronium in water. So that concludes our kind of introduction on what acids and bases and pH is. Okay. In the next video, we're going to calculate some pH and pOH of some solutions.